Today's lesson, we're going to look at limits at infinity. So far, we have considered limits as x approaches a number, case in point C. It is also important to consider limits where x approaches positive infinity or negative infinity, which we refer to as limits at infinity. In applications, limits at infinity arise naturally when we describe the long-term behavior of the system. For example, if you take a look at this function g of x, and you notice it has a couple of maximums and minimums, but as you follow the function to the right, in other words, going to positive infinity, you'll notice that the function appears to level off. There's a horizontal asymptote here at positive 7. And so if I were to ask you what the limit of this function is, the limit of g of x, as you approach positive infinity, what does the function appear to be leveling off to? The answer to that would be 7. So its value would be 7. The limit of g of x as you approach negative infinity, it appears to be leveling off at positive 3. So its value would be positive 3. So really what you're finding is horizontal asymptotes. So limits that go to infinity help you determine if there are horizontal asymptotes of your function. Case in point, this one, y is equal to e to the x. You might recall what the e to the x function looks like. It's this exponential graph right here. If I ask you to tell me what the limit of e to the x is as you approach negative infinity, you would notice that it seems to level off to 0, which implies there is a horizontal asymptote right there at 0, and so that limit would be 0. But however, if you look at the right-hand side, if you follow the function as x approaches positive infinity, in other words, going to the right, it increases without bound, and so that would be simply positive infinity, which means that my limit does not exist. Specifically, it's positive infinity. Now, in both of these cases, at the sine function, you'll notice that sine of x oscillates between positive 1 and negative 1, so the limit as x approaches infinity for sine of x clearly does not exist because it doesn't actually attain any value. It's oscillating between 1 and negative 1, and also as you go to negative infinity, it's oscillating between negative 1 and positive 1, so it does not exist either. So there are cases where limits at infinity do not exist. Now, for our conversation, we're going to be looking at 3 rules for limits that go to infinity. The first is you look at the degree. If the degree is bigger in the denominator, then the limit equals 0. If the degree is bigger in the numerator, then the limit does not exist. If the degrees are equal, it's the coefficient. So for this example, it says the limit as x approaches infinity of 20x squared minus 3x over 3x to the 5th minus 4x squared plus 5. Notice the degree is 5 in the denominator and 2 in the numerator, so it's bigger. The degree is bigger in the denominator than it is in the numerator, so I know the limit of this would be 0. I could probably graph this, and I would probably see that my function does level off at this y is equal to 0 value. So it would mimic kind of like a horizontal asymptote as the function's leveling off. For the next one, the limit as x approaches infinity of 3x to the 4th. Notice that the degree in the numerator is 4 in the top, and the denominator is 4 in the bottom. Those degrees are the same, so this limit will equal to simply the coefficients, which would just be 3 over 7. For the next one, notice it says the limit as x approaches negative infinity. It really doesn't matter in the context of this problem because notice the degree in the numerator is 8, the degree in the denominator is 3. It's bigger in the numerator, so that means the limit does not exist, which means it would probably be either positive infinity or negative infinity. And you could quickly determine what that would be, simply just simplifying this a little bit. We know that 3x to the 8th over 7x to the 3rd, so if you think about x to the 8th over x to the 3rd, that reduces down to x to the 5th. X to the 5th, notice it's an odd degree, so it would be falling on the left and rising on the right. You know, it would have that shape. You remember that from pre-calc. So if I was asked to find what the limit is as x approaches negative infinity, so I know it's falling on the left, so the answer to that would be negative infinity, but that's still the same thing as does not exist. For the next one, the limit as x approaches negative infinity. Notice that the degree is in the numerator, then the denominator. So again, this would be does not exist. And if you wanted to get into the question of whether or not this is positive or negative infinity, the same trick as before. So this would be x to the 7th over x to the 3rd. Just clean that up, you get x to the 4th. It's an even degree. So that means it's going to be rising on the left and on the right. Something's going on between there, but as you approach negative infinity on your function, notice it's going up, so that would mean it was positive infinity, but it still does not exist. For the next one, the limit as x approaches infinity, notice the numerator is 7 over 2. Keep in mind that that's approximately, that's not approximately, that's the same thing as 3.5. The degree of the denominator is 2, so it's definitely bigger in the numerator, so that again does not exist. And if you were to, argue about if this is positive infinity or negative infinity, you could graph this function. That would be fine, and you would discover that for this problem, you would end up getting positive infinity. You could do the same trick as before. X to the 7 over 2 over x squared simplifies into x to the 4. That would be 3 over 2. And so then that would basically look like kind of like this, kind of like that function right there. And then as you approach positive infinity, you notice the function is increasing without down, so it will be positive infinity, just like we talked about. A couple of more examples, final examples. If you were to look at a problem, say like this in the top left-hand corner, the limit as x approaches infinity of x squared over square root of x cubed plus 1, you could treat this as, that's the same thing as x squared as, this is the square root, so that you could think of this as x to the 3 halves plus blah, 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 but we only care about really the coefficients. But notice the degree is bigger in the numerator, and so if I go back, if the degree is bigger in the numerator, then the limit does not exist. So I would know that this limit does not exist, and you could apply the same trick to that, and it would obviously give you positive infinity for that answer as well, because if you did x squared over x to the 3 halves, that would give me x to the that would give me x to the 1 half, which is the square root of x. So then that is that shape, and sure enough, as you follow that curve, it's going to positive infinity. So that would be positive infinity, but still, this does not exist. For the next one, it's the limit as x approaches infinity of 12x plus 25 over the square root of 16x squared plus 100x plus 500. You can clean this up a little bit. Remember square root, so you could see this as square root of 16x squared, so that would be plus or minus 4x plus blah, 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 right? Because you can take, well, you were trying to simplify the rest of it. But notice that the coefficients are the same, but would be 12 over plus or minus 4, so that would end up giving me plus or minus 3. So you're probably thinking, well, where does the plus or minus come from? It all dictates on whether or not you're asking for the limit as it goes to positive infinity or the limit as it goes to negative infinity. If I wanted the limit as x goes to positive infinity, the answer would just simply be positive 3. That's what the answer for that one. So it's the exact same problem. If the limit as x approaches negative infinity, that would simply be the negative 3 part of that one. So that's where those answers come from. And if you were to really graph this function, you would notice that it would have a leveling off at 3 and negative 3. So just to show you what this graph looks like, if you were to graph that function, this is what the graph would look like. And if you notice, it does level off as you go to positive infinity, it levels off to positive 3. As you go to negative infinity, it levels off negative 3. That is limits at infinity.